So I listed a few frequently asked questions that I can think of, and you can. I think this is a time actually. I'm very willing to collect some questions if you have. Yes. So what are the target audiences and prerequisites of this course? So I want to emphasize that this course is intended for international students as one of the mandatory courses, though domestic students are also allowed to take. This course, I think, may be a little bit simpler than the Chinese counterpart. I mean, offered by Professor Xiaozhen and Professor Wang Xiaoying. But I think the reason is that maybe the assignment problems are a little bit easier, and actually a main part is actually doing final projects. So I guess maybe from this perspective, the course may be a little bit simpler than the Chinese counterpart, though I think the difficulty is in general still at graduate level. I think the style of this course is maybe probably more like the courses they're going to offer like in some university internationally. And actually the style is slightly different than the Chinese counterpart that is also offered in the same semester. So about like prerequisites, I think undergraduate level introductory knowledge about design of basic algorithm, maybe for instance, like quick sort, merge sort, etc. Just like a few very basic examples. Like basic knowledge are preferred. I think I will try to make this class self-contained, but maybe some very basic concept may be skipped. And if you have any questions, you just feel free to ask me like when I introduce something that you don't understand. So is this course purely theoretical? So one of the students just asked this question. So this course will focus on the theory of algorithm design, complexity theory. And interested students are encouraged to program the algorithm discussed in lectures and assignments. So how well will the grades be given? I guess as long as you finish assignments, final projects, and final exam, I will try to give you good scores because this in general like a graduate course, and I guess like professors shouldn't be very harsh about like, this course. So any other questions?
I just have a quick question.
Sure.
I actually haven't never read this book before because I think most of the people that are giving the class they use non-textbook called CO student.
Yeah, I heard of that.
Yeah, so what's the major difference between the two texts?
Yes, I think the book you mentioned focus more on like the programming side and like basic data structure. But I think basically for this course, that's like a course focused on theoretical computer science and also a graduate level course. We will really go into the thoughts about design algorithms. So I think in later of this class, we will find out, for instance, we are going to talk about some graph algorithms, but maybe I won't talk too much about how you are actually going to utilize data structure to implement these graphs. But actually, we are going to design some sophisticated algorithm that can really solve some interesting problems. Like the focus, I mean, like data structure, I mean, algorithm design, there are slightly some, maybe we can like sense a little bit about the difference.
Is there going to be a lot of problems on NP later?
We will introduce NP hardness and there are going to be assignments on. Yes, you're welcome. Any other questions? Any questions online? Yeah, just for online students, we cannot see it's basically this book. Okay. So this is a tentative syllabus. I guess this is really the first time that I teach this course. So I'm probably not super experienced about like what is going to be covered about the topic. But I think basically, I think the very important thing is that we will, of course, in this class and also the next class, we will at least like give you some warm-up that basically we will introduce the basic of algorithm analysis. Maybe we will discuss about like the problem of stable matching, like Beagle notations in general, asymptotic notations, etc. And I think basically we will, a very important chunk of this class is that we will offer four very important ideas of design algorithm that basically some thoughts in general you find very helpful when you want to design algorithm. Those are like basically a greedy algorithm, divide and conquer, dynamic programming, and network flow. So those are like four very typical kinds of ideas that you can find very helpful when you design algorithm. And I think before that, we will give you a very detailed introduction about like graph algorithm, because graphs are just so important in computer science in general. And I think in later part of the class, as one of the students asked, I think a very important we will introduce complexity theory about like what is P, what is NP, what is the P versus NP problem, etc. We will introduce complexity theory. And also, depending on whether we have enough time or not, we will introduce a little bit more advanced algorithm like approximation algorithms, randomized algorithms, etc. So I saw one of the students actually, online students just asked like whether the slides will be posted online. Yes, it will be posted online, but actually, basically for this introductory lecture about like the requirements, all of the things has been posted on the course website. So the goals after you learn this course is basically you want to have a basic understanding about algorithm design, complexity theory, and also you want to be able to conduct research in, if you want, you can conduct research in theoretical computer science. So any questions? So maybe let's actually take a quick look about the course website. So this is basically the course website. We can see that basically algorithm analysis and complexity theory for 2022 Peking University. And as I just mentioned, that basic information of the things that I showed in the slides actually all posted here. And actually evaluation, the schedule, tentative syllabus, assignments like project. So I will post the slides again on our course website, but basically the information are here. Okay. Sure.
Will our project be significantly harder than this? I think the latest paper they must be harder than basic algorithm.
Yes. Yeah, I think for most algorithm that we are going to introduce today is probably they have been discovered for dozens, because they're like relatively basic algorithms. I mean, speaking of difficulties, of course, I guess the up-to-date research should be more advanced than like textbook things. But I guess it depends on your own control, because basically you see like assignment 5 is going to due on week 13, and in general you have relatively I think enough time to maybe think a little bit more along that. I think my expectation is that it is probably supposed that the final period is a little bit going to be a little bit, at least a little bit, or expectedly more evolve and advanced compared to the course material, because you're supposed to really actually delve into a specific topic and have like a more deeper and better understanding about it. Only speaking of difficulty, but on the other hand, I mean, if it's just like a 10 pages final project, is on the other hand should not be too evolved. I guess maybe you want to like try to have a balance when you actually work on the final project, and you have like maybe some like you're not so sure about how to control this, about like the subtlety around this. You just feel free to ask me when you work. You're welcome. Any other questions? Okay, so I guess this is probably the time that we are actually finish like the introduction. Maybe let's actually go into the technical details about like the basics of algorithm design. Let's get started. Oh, there is one question. So what level of programming is required for this course? Do we have any assignment or tests need to implement codes? There is no requirement. I won't have any problem require any coding of the results. So this course is like a purely theoretical computer science course, and we don't have any coding requirement for the assignments and also for the final exam.
Someone also asked whether the
Yes. I think currently, I think the TA is recording the lecture, and after this, we will probably, I think maybe one idea is probably to save this maybe in the PKU disk, online disk, and maybe share the link to the PKU students. Yeah, this is in our plan. Any other questions? Okay, so let's get started maybe to the technical part of the lecture. So for the rest of today's lecture, we will basically cover some basics of algorithm design. I think at the beginning, I will talk about a problem called stable matching, and then I will talk about asymptotic notations and also graphs. So let's begin. So what is the stable matching problem? So let's begin. So this is a simple example. Stable matching. So I guess you are actually currently a graduate student, and maybe you're actually relatively junior graduate students, and you encounter the situation of maybe applying to graduate schools. So this is just like a problem, maybe for instance, that we have n students. Like students, I just represent them by S1 to Sn, and also n graduate schools. So because we are talking about graduate schools, maybe let's represent them by like G1 to Gn. So for this problem, I mean, in general, I mean, graduate school application is super complicated, but let's just consider a simplified problem that each school admits exactly one student. So I guess when you apply to graduate schools, and maybe also on the other hand, when graduate schools select students, I think there are definitely preferences. So I guess maybe let's make an assumption that each student list schools in order of preferences from best to worst. And I guess we can make the same assumption for the graduate schools. So I guess maybe let's just like copy this. So each school is students in order of preferences from best to worst. So you see, like we have n students in graduate schools, and this comes to a very natural definition called perfect matching. So for the perfect matching problem, I mean, we just want to consider a case where each student gets into exactly one school. And of course, on the other hand, each school is going to get exactly one student. So because we have preferences of, I mean, so some students like maybe one of the graduate school upon others, and maybe some graduate school like one of the students upon others. And in general, there is a sequence of the preference list. I think a very important thing that we really want to, if we want to design algorithm of this, like a toy problem of like a graduate student, grad school application, I think a very natural definition maybe we can think of is the stability. So how to formulate the stability? I mean, if some school admits some students that the school really doesn't like, or maybe some students really go to some graduate schools that the student doesn't like. So that is not ideal. So in general, I mean, we consider the case where we have a matching. An unmatched pair is unstable. Oh, so you mean the, is this better? Oh, okay, okay. If both SI and GJ prefer each other. Oh, sure. Is it looking better? Maybe, let me see. Okay. Okay. Prefer each other to the current partners. So I guess this is a little bit abstract to digest, but this is just like a formal definition we want to give for stability. Maybe let's just see one very simple example. So let's assume that currently, here is an example. So currently, maybe Alice is admitted to Tsinghua University, and maybe Bob is maybe admitted to Peking University. But there are actually natural scenarios. Maybe, for instance, you assume that, and maybe, for instance, like Alice prefers PKU than Tsinghua University. And maybe also on the other hand, it can be possible that PKU prefers Alice than Bob. So I guess in this case, you can see that, I mean, I'm actually emphasizing that there is an unmatched pair because actually in Chinese, there is like a saying that like people actually always think about when you actually didn't get it. I mean, in Chinese, 得不到的永远在骚动. I mean, just like that. I mean, in general, if you want to consider like an unmatched pair along this, I mean, for instance, like Alice is matched to THU, but Bob is matched to Peking U. But really, I mean, this is not stable because Peking University actually prefer Alice than Bob. And actually, Alice also prefers Peking University than Tsinghua University. So in this case, I mean, a very natural scenario is that it will turns out that Alice is probably going to be matched by Peking University, and maybe Tsinghua University is maybe need to admit another student, and like Bob is going to find another graduate school. So this is very natural in the problem of like finding a matching. And in general, we want to be careful about, in general, maybe we not only want to find like a perfect matching, but hopefully we are going to find a stable matching. So for stable matching, it's just like, of course, you can just imagine it's just like perfect matching with no unstable pairs. And a very natural goal here is going to, given the performance list, actually use black here. Given the preference list of n students and schools, find a stable matching if possible. So is this definition clear to you? Do you have any questions? Okay, so let's just think about this problem. So if we encounter such kind of like graduate student problem, what is like a natural algorithm you want to think about? I mean, for such kind of things, you can always find like, you can maybe try to like, try other strategies. But I guess there can be something very efficient, because if you keep find some unstable matching, I mean, if some kind of pair obviously exists, such kind of, for instance, Alice PKU pair, then this is not very helpful. And I think in general, you want to be like a little bit strategic about how you want to design an algorithm. In general, hopefully, like this kind of like a switch between unstable pairs does not happen too many times. So I think because we are actually introduced, this is the very first problem that we introduced in the class. I guess I won't really give you a long time to think about this, but maybe let's actually think about an algorithm that actually proposed to solve the problem, and let's see whether this algorithm works well or not. So this is an algorithm called the Gale-Shapley algorithm. And the strategy can be summarized by like a short phrase called propose and reject. So what do I mean by that? So maybe let's just write down the algorithm, and you will probably get the intuition of the algorithm. So initially, we just initialize each student to be free. Well, some student is free, and hasn't proposed to every school. So I think in general, if you want to think about such kind of problem, there are going to be some iterations that maybe you have to have some mechanism that you want to assign some students to some graduate schools. And I guess the strategy here is just like we use this kind of while loop. And as long as there is some student hasn't found a graduate school, and if some student hasn't found a graduate school, there are also some graduate school didn't find a student because they have the equal number. So we just consider such kind of while loop. And what is really important is what we are going to do inside the while loop. So this is going to be something like that. So while some student is free and hasn't proposed to every school, we just choose, of course, we just need to choose, first choose such a student as. And as we just mentioned above, so each student actually leaves schools in order of preference from best to worst. So maybe let's just denote G to be the first school on S list to which S has not yet proposed. I guess this is very natural because you want to think about algorithm along this line. You choose a student that has not been proposed to every school, and then I mean the students always want to find the school that the student really likes. I mean it's just very natural that you consider such kind of command that you consider like a G to be the first school S lead to which the student has not proposed. But there are actually going to be different scenarios about the school. Maybe for instance, like if the school is free, I guess this is really a scenario that we want. I mean, if the school that the students like the first on the student's lead to which the student has not proposed, if the school is free, then we just assign the student to the school. But on the other hand, there can also be the case else if G is not free. But I mean, if the school is not free, then that means currently the school has been assigned to a student. But maybe if the student S is lucky that G is not free and G prefers S to the S as currently admitted student. And I guess in this case, you see that the student S, it is not assigned. And for the school G here, actually the school prefers the student S compared to the current student it is assigned. Then it is very natural that we just assign the students to the school and set S prime. So the S prime is the previous student that is assigned to the school G. We just like set it to be free. And else, and that is the worst case. The worst case is just like, I mean, which means that G is not free and S prime is actually already better than S from the perspective of G. Of course, G is going to reject S. And this actually makes an error. Let me see. Okay. Yeah, I guess now you can see the whole algorithm. So I guess this algorithm, which is called the Gale-Shapley algorithm, is probably something very natural. I guess in general, you actually, when you want to make up the match, it's just like something strategically how you are going to match the students and the graduate schools. So we just like apply like a while loop from the perspective of students. I mean, if some student is currently free and hasn't proposed yet, and just like try the first school that is already in the actually in the school the corresponding student's lead who has not the students has not yet proposed, and just try that, and depends on whether the school is free or maybe it's not free, but like actually the school prefers the student S rather than like the student S prime that is currently assigned to the school, and then just like the G is going to switch, or maybe like else it's just like the student S is not preferable compared to S prime, then G we just like rejects that. So this is the Gale-Shapley algorithm. So is there any questions about the algorithm? And also any questions online? Okay, so guys, let's continue. And also for online students, you can just feel free to ask further questions. So I think, I mean, during the break, I answered a few of them. And I think there are also some further questions. So, I mean, some students like my lecture, thank you. Yeah, I saw some questions saying that, can the algorithm also consider equal priorities by one student? Yeah, that's a good question. So in this algorithm, I mean, for this very basic case, we consider a case where there are like strict preference. I mean, like a graduate school, maybe you just like given two students, like graduate school, strictly prefer one than the other, or maybe given two graduate schools, a student exactly prefers one compared to other. Yeah, I guess for equal cases, you can maybe for instance by like fixing the definition. I mean, if for the equal case you don't like bother to like switch, I mean this does not like brings unstability, then actually the current algorithm is still fine, because I mean it probably depends on how you are going to define what is unstable or not. Yeah, but I think for making this like a toy case, we focus on a case where there's strict preference both on the student side and also on the graduate school side. Okay, so let's actually going to give some a more detailed understanding, maybe some rigorous understanding about like the behavior of this Gale-Shapley algorithm. So we are going to make some observations. So first observation. So I guess this really sounds trivial, but after we have written down all of the observations, we will find some non-trivial things are actually going to happen. So the first observation is that students propose to schools in decreasing order, in decreasing order of preference. I guess this is just very natural because when we see the algorithm line here, so as long as maybe a student is currently in this while loop, it's just like the students has like a list. I mean, the list is just like the first school on the student's list to which the student has not proposed yet. So it is highly possible that the same student as come into the while loop again. So this is an important point that you want to keep in mind, that a student can go into this while loop again. Maybe for instance, like, of course, in this, maybe for instance, we go into this else if line. The student's S prime is of course going into at least once in this while loop again. So the students can get into the while loop again and again, but because the school, I mean, there is like a list of this, and each time it is going to have the list, and it's going to only choose the first school that is in the student list. So this is actually something going down, and actually the students propose to schools in decreasing order preference. And actually, this is going to be even clearer that after I read the observation 2 here. So once a school is matched, it never becomes unmatched. So I guess this is just natural from the point of our algorithm. So I think the while loop, we are talking about the students. But actually, when the schools are getting matched, I mean, it's just like in this if else on those conditions. So in the if case, I mean, you see like the school G here, it is perfectly free, and then it is assigned. So in the else if case, I mean, G is not free, and G prefers S to the student S prime currently admitted. So in this case, G is not free because G actually switched the S prime to S, which the school G is actually prefers correspondingly. And in the else case, so G is not free, then G just rejects the students. So in any case, you see that actually the graduate school G is never going to get free again. This is actually why we say this observation too. Once a school is matched, it never becomes unmatched. And actually, we can give like a further conclusion, maybe like intuitively, actually, the school, it only trades up. So what do I mean by that? So you see like when G is actually making a switch. So in this case, I mean, if originally G is free, then we just assign the student S to the graduate school G here. So in this else if case, so we see that in this case, the school G is actually prefer the student S compared to the originally assigned S prime. Then G just like we correspond assign S to G. So S is better than S prime. So that is the reason why you see actually the school G is actually trades up here. And on the other hand, if it is the else case, so if the S prime is better than S, then G just rejects S. So the school never trades down. So this is actually a very important intuition, actually compared to observation 1 that we just explained, that students propose to schools in decreasing order preferences. So let's just look at again in this line. So this line, the G equals to the first school on S lead, to which S has not yet proposed. So if previously there is like a school that the student actually has proposed, it can only go down like this accordingly. So this is actually going to be a very important thing, and actually we are actually going to make the claim 1 here. So the claim 1 here, the algorithm terminates after at most n squared iterations of the while loop. So this is a question raised by one of the students that if I just I give you the Gale-Shapley algorithm, it is not apparent that this algorithm actually going to be terminated. But this is actually something we can infer from these observations that the algorithm actually terminates after at most n squared iterations of the while loop. So why is this the case? So we just gave a brief proof here. Each time through the while loop, a student proposes to a new school. I guess this is apparent because in the while condition, we are saying that some student is free and hasn't proposed to every school. And then here we consider the G here, like to which S has not yet proposed. Has not yet proposed just means that the student is going to actually propose to a new school. And actually each student from this perspective, there are n schools. There are n schools. Which infers that each student goes into a while loop for at most n times. And there are n students, which suggests that just like the number of is going to be smaller than n squared. So any questions? Okay, so I guess the complexity of this algorithm, although it is not totally apparent, but like based on these two relatively simple observations, you can see that the algorithm actually is going to terminate after n squared iterations of the while loop. So next claim is going to be a little bit more sophisticated. All students and schools get matched. This is very important because after all, we are talking about stable matching. So the first step of being a stable matching is that it should be a matching. I mean, we don't want to have the case where like a student or maybe like a school is left over. This is not what we want. But we want to prove that actually this Gale-Shapley algorithm can satisfy the promise that all students and schools get matched. So let's actually prove this. So the proof is actually also intuitively, we can maybe, for instance, just assume the contrary. Maybe let's just assume that student SI. Maybe this is an unfortunate guy that is not matched. Let's see what is the contradiction that is going to happen. So at least one student is not matched. This just means at most n-1 students are matched. But on the other hand, we know that since there are n schools, and as we mentioned, each school can only admit one student, there exist. So one thing that I want to emphasize is that in this class, I think we are going to use some symbols. So we read this for exist, and we read this for any. So if you're not familiar with basic logic, so this is basically some notation we are going to use throughout the class. So basically, since there are n schools, basically there exists a school GI, maybe not GI, I mean, we have used index I here, but a school GJ is unmatched. So let's see what is the contradiction here. So we are going to first use the observation 2 here. So once a school is matched, it never gets unmatched, it only trades up. So what does it mean here if you look at observation 2 here? So if there is a school that is currently unmatched, we got a conclusion that GJ was never proposed to. However, on the other hand, let's see, I mean, we want to consider the claim 2 here that basically the contrary we assume is that even after like the termination of the Gale-Shapley algorithm, the student SI is not matched. This is just a contradiction because you see like in the while loop, some student is free and hasn't proposed to every school. So the contradiction point is that SI has not proposed to GJ but Shapley-Gale answer. So we get this contradiction. Is this clear to you? Any questions? Okay, so I guess basically you see the observation 1, observation 2 here. They're actually relatively simple observations, but if you want to think about things rigorously, I mean, we make such claims, you can see actually the logic here is also, on the other hand, we can really give some interesting results. And I think the final thing is that we want to prove is that we have already shown that finally, after the ends of the Gale-Shapley algorithm, there are actually all students and schools get matched. But we are talking about stable matching, and let's actually prove that. So the final thing that we actually want to claim is actually our final goal is that we want to show there is no unstable pair. So we prove this by contradiction again. So if it is contradicted, then we are going to have like a, suppose like Si Gj is unstable pair. Yeah, so due to the definition of unstable pair, I mean, we are talking about here. So we want to here, as we just mentioned, that Alice PQ is basically an unstable pair. So this unstable pair means that Alice has currently been assigned to another graduate school, and the PKU has been actually assigned to another graduate student. So this is basically something we want to specify. That basically this means that if maybe let's just say like Si is currently assigned to GL, and Sk is assigned to Gj in the matching, then since we are talking about unstable matching, so it must be the case that Si actually prefers this a Gj than GL, and actually on the other hand, from the perspective of graduate schools, then Gj should prefer Si Sk. So this is the, just like we follow very basically by the definition, or maybe let's similarly, maybe let's draw like something similar to this Alice on THU about PKU case. It is basically something like Si is currently mapped to assigned to GL, and Sk is actually assigned to Gj, and we are actually worried about this unstable pair. Basically like this. So how we are going to continue our discussion? So we are actually going to, based on the case that because you see actually when we run this Gale-Shapley algorithm, it is very importantly that we want to talk about the while loop and the conditions inside. So basically we make the discussion like this. So we consider the first case where Si, the student in this while loop, never proposed to Gj. And the other case is then the student actually proposed to Gj. So we are going to try to find some contradictions along this. So what is the issue with the first case that I never proposed to Gj? It actually like this. So because students propose in decreasing order of preference, this is just the first observation. Si actually should prefer GL to Gj. So you see, like basically for this case one, we get a contradiction here. But also on the other hand, for case two here, for the specific case where the student SI proposed to GJ, there is actually another contradiction that we are going to incur. That on the other hand, the situation is like since XI GJ is currently not a current pair. So GJ actually rejected SI. So because SI GJ is not a current pair, and basically by the discussion in observation two, the graduate schools only trace up. So it must be the case that GJ actually rejected SI. So it can be the case maybe right away. I mean, by right away, I mean, it is probably going to, right away is just me in this L, in this line of L that basically, maybe like at that case, the school G is actually prefer this S prime instead of S. So basically for this L's line, the last line here. So this is what I mean by right away, or maybe it can also be the case or later. I mean, it's just like by this propose, it's just like ever propose, but the rejection can actually happen right away, or maybe later, or maybe in the case where actually SI is unfortunately the S prime, but the graduate school traces up, and then it's just like the graduate school abandoned the student SI here. But this means in any case, I mean, if this kind of rejection, I mean, this kind of right away or later condition, you can actually see that this means that, sorry. This means that actually GJ prefers SK than SI. Because like school only trade up. So in both cases, we got a contradiction. Any questions?
Is this algorithm have and student schools?
At least not the original version of the Gale-Shapley algorithm. I think you can see that basically, so the student asked about like whether if there are like an equal number of schools and the students. I guess at least there is going to be an issue. I think it got stuck. So maybe let me open this.
If there's anyone that's left not considered student, because each preference is not resolved.
Yes. So you mean like in the case of equal number of students or?
Like this claim three still works if some net is not matched.
I think at least we need some like really non-trivial changes because the claim two will be, of course, not going to be true. We won't have the claim that all students in school gets matched because actually you see like in this discussion. So for instance, if like there are more students than schools, then basically, I mean, it can just be the case that all schools are matched and there are students left. And I guess this like algorithm of this Gale-Shapley algorithm is just going to be broken.
I think this is also the case when you have two persons with the exact same.
Yes.
Like one of them will not. Because it's kind of true between the two.
Yes, but I think you want to be then you want to be careful about the definition of unstable pair. I mean, if like for instance, if the students have like maybe like for instance, if a school has equal preference between two students, and maybe in this it depends on how we define unstable, and maybe if in this case it does not constitute like unstable pair because it is okay actually, it gives them same value, then actually the algorithm, the Gale-Shapley algorithm still works. So you just like each time you find like an equal value, you just like randomly pick one of them. This does not influence the stability of it. Yeah. Any other questions? I think maybe one question not related to algorithm. Do you think I should maybe write a little bit larger? Is this a little bit smaller maybe in the backlines? Okay. Have you ever tried to, but I think maybe especially for case one, case two is a little bit squeezed. I will try to write larger in this writing. Okay, so let's make a summary of this Gale-Shapley algorithm. So basically, a summary is that this Gale-Shapley algorithm actually at least works for this very toy problems of stable matching. That's Gale-Shapley algorithm. Guarantees to find a stable matching. Oh, yeah, let me close this. Any problem. Instance, I mean like graduate schools, students, and their preferences. And the algorithm runs in, oh, sorry, at most n square iterations. So we are going to make a summary here. So this basically finished the discussion about the stable matching problem and the corresponding Gale-Shapley algorithm. So this is basically like a very like a showcase, like a toy problem that we are going to study in this class. So you see, like basically in this class, we are actually talking about some really algorithm design problems. So we have some models. I do believe that in general, real world like graduate school applications should be much more complicated than this problem. But I think a very important thing is that you want to model some problem. So basically, this is such kind of abstraction, like into an algorithm design problem. And the goal is that we want to give some rigorous guarantee. So this is the general thought that in general, we want to have a good understanding about the theory of algorithm, and in general, how good can we actually give algorithm to solve some specific kind of problems. So I think this is after I give you this very a beginning case for this stable matching problem. And I think next we want to in general, we want to have a more a detailed characterization. I want to talk about like maybe we have some fast algorithm, some good algorithm, but what is good? What is fast? So basically, we want to give some more detailed characterization. So this is basically something about like characterization of the complexity of algorithms. So this is basically in general achieved by this so-called asymptotic notation. So in general, as I just mentioned, that we want good algorithms. Good is really too broad, but in general, we want, let's say, fast or maybe efficient algorithms that run quickly on inputs, that run quickly on real inputs. So this is really, I guess you can understand from this English discussion, but as I just mentioned, we want to make everything more rigorous. So what is the effort of making this rigorous? So in general, a very important thing that we are going to study in this course is that we call something as the worst case running time. So because as we talked about this, I think maybe for instance, you look at this summary discussion. So we talk about like any instances, I mean like graduate schools, students and their preferences. But what is very important is that for the scale-Shapley algorithm, after we discuss about like this proof, it always works. So in general, I think we want to be more rigorous about like for any instances about like for every instance actually what we can do here. So especially, I mean, if we want to talk about the running time of algorithms, so basically we want to consider like the worst case running time that we want to obtain the bound on the largest possible running time of all the instances. Of the algorithm. On input of a given size. So typically we have because we are actually going to talk about some real problems, so we are going to have some inputs. So in general, this kind of input, so for instance, I mean, we talk about this stable matching problem, although we do admit this is really like a toy problem, but we have n schools and n students, and this n is basically the size of the problem. And you will later see that in a lot of places in our class, we will actually use this size. Maybe for instance, we just like write size n. This n can be a lot of different things maybe for each problem, but you can always imagine that for a problem, it can be large, the scale can be large or small, but we always have some kind of way that we want to characterize the size of the input. Maybe let's just call it n here. Yeah. So this is something that we want to emphasize, that we talk about the worst case running time. And actually we want to, there are some remarks we want to make that the worst case running time can be conservative. Of course, it can be, because we are talking about the worst case. I mean, the best case running time, maybe just the problem can be trivial for some very specific instances. But in general, the worst case running time can be conservative. But we want to make sure that even for the worst case, it still works. So this is basically that, but generally captures efficiency in practice. And this is actually the main focus of this course. So there are some definition, maybe not the worst case running time, but you might heard of the word that some algorithm has good average case bound. But in general, in algorithm analysis, you want to be careful about what is called average case. It is average upon what? What kind of average instances? But in general, for instance, if we are talking about like an average case distance on the Shapley-Gale problem, what is actually doing averages on what kind of like schools and like students? So there are always something debatable about like, well, what kind of randomness and what is the average range that you're actually going to work upon that. But actually, the easy thing for the worst case running time is that for arbitrary, I mean, as long as we have a clear model for this a stable matching problem, we have graduate schools, graduate students, and the algorithm works. And I think to actually not bring the story into a more complicated scenario, that is actually also one of the most important reasons why we want to study the worst case running time in this class. Okay, so after having this definition of the worst case running time, I guess we then want to maybe want to have a better understanding that which algorithms are efficient. I mean, in general, you want to thought about efficiency, maybe efficiency of some computational problem. This is of course quite different. I mean, maybe for instance, if I compute something, maybe like a number of 100 digits multiplied by 100 digits, I guess this is just going to be too difficult for myself. Or maybe if you just consider like a computer, maybe it's just like a calculator, or maybe like the Tianhe super computer. I guess their capability is in general very different. But in general, I think we want to basically from like an algorithmic perspective, and in general, if we want to do everything rigorously, I mean, in general, this kind of efficiency, we probably need to think about this in terms of the end here. So basically, with respect to this input size, and basically how large or how small, and basically in terms of this n, that actually how good or how bad we can solve the problem. So in terms of n. So I think one thing that we want to emphasize is that in a lot of algorithm, actually in a lot of problems, there is always a problem called the brute force. You just try all the solutions. I mean, this sounds doable, but this is actually not so good in general, because the point is that typically, let's say it typically takes time at maybe, for instance, like 2 to the n, or worse, for inputs of size n. So maybe let's just for instance, let's just take a look at the stable matching problem. So I guess as we mentioned for this Gale-Shapley algorithm, it actually the while loop only runs for n squared iterations. But of course, one thing you can do is that, okay, I don't know Gale and I don't know Shapley. I just like try all of the things. I mean, there are n students at n schools. The worst thing, I mean, you just like brutally check like all matchings between students and schools. So basically, one good thing about the Gale-Shapley algorithm is that after we know that this algorithm succeeds, it actually proves one thing, that there always exists at least one stable match. So keep this in mind. So in general, I mean, given you know that there always exists such kind of stable matching, you can actually brute forcefully check all the possible matchings. But the number of matchings is n factorial. So how large is the n factorial? So n factorial, if you're not familiar, is just n times n minus 1 times n minus 2, etc. So there is a formula called the Stirling's formula. Saying that n factorial roughly equals to square root of 2 pi n times n over e to the n. And actually, this is even much larger than 2 to the n, because you're talking about n over e to the n instead of 2 to the n. So I guess you can see, I mean, if you're like really powerful, and if you don't mind anything, then basically brute force can actually solve a lot of problems. But this is not really the algorithm that we want, because it really takes too many time, too many number of trials in general, too much time that we can solve all these kind of problems. And of course, we want more efficient algorithms. And this. So in general, this probably brings us into a mind that in general, I mean, probably n squared is acceptable. But in general, I mean, we talk about some brute force algorithm, and in general, maybe for a problem of scale size n, then probably like 2 to the n or maybe n factorial, this is too large. So we get some sense about like maybe what kind of things, I mean, n squared is potentially like good algorithms, like 2 to the n or maybe n factorial. There are probably, if you have algorithm like that, there's probably bad algorithms. So what is a good thing then we want to make sure that we can like safely describe as efficient algorithms? So in theory, we consider something like this. So we consider something called a scaling property. So when the input size doubles, the input size doubles. I mean, by doubles is that instead of consider a problem of input size n, we consider a problem of input size 2n. Then we have the scaling property if the algorithm only slows down by a constant factor. So this is what we call a scaling property. I guess this sounds very natural, because in general, I mean, if we have an algorithm, I mean, if the problem size doubles and you really pay a lot, this is probably not something you want to see. And maybe, for instance, let's talk about a case where it is 2 to the n. So if it's an algorithm with cost 2 to the n, and if you double the problem size, that's going to be 2 to the 2n. But the 2 to the 2n actually equals to 2 to the n times 2 to the n. So the thing that you're actually timing here, this 2 to the n is in general quite large. I mean, this is not something that satisfies the scaling property because the algorithm is going to be slow. Actually, it is going to be more than a constant. Actually, it's actually going to be slow by a factor of 2 to the n. This is really something quite significant, and we don't want algorithm like this. But what kind of algorithm satisfy this property? Maybe let's just, for instance, like take a look at this algorithm with cost n squared. So if an algorithm has cost n squared, then 2n squared equals to 4 times n squared. So this is actually good, and actually an algorithm with cost n squared satisfies the scaling property. So in general, this comes to a very natural definition called polynomial time algorithms. So in English, this poly is just like a prefix that in general represents like a multi. I mean, can be many things. Because I think the polynomial, this word here has some specific meaning. So for instance, if you look at the algorithm with cost n squared, so 2n squared equals to 4 times n squared. But how about like an algorithm with cost like n cubed? I mean, an algorithm with cost n cubed, you just like make a computation here. I mean, 2n cubed equals to 8 times n cubed. So we are talking about scaling property. I mean, this only slows down by a constant factor. So 4 is a constant and 8 is also a constant. So this n squared is good. So in general, the poly here, we can just imagine that basically in general, I mean, maybe it's not like n squared, maybe not n cubed, but in general, actually, we want to consider the case where there exists constants CD larger than 0 such that on every input of size n, its running time is bounded by c times n to the d steps. So this polynomial time, you just look at the things here where the c and d, they are constant here. And in general, we can easily see that this satisfies the scaling property. In what sense? We just consider like c times 2n to the d here. Then this is basically c times 2 to the d times n to the d. But we know that cd here, they are constants. And basically, we want to make sure that basically this 2 to the d is a constant and everything is good and actually satisfies the scaling property. And in general, I guess after making all this kind of discussions that we are probably good with like n squared and we are probably not good with like 2 to the n, like n factorial. I think throughout this course, we consider an algorithm is efficient if it can be solved in polynomial time. A problem can be efficiently solved if there exists an efficient, basically a polynomial time algorithm for the problem. So let's just write this down. An algorithm is efficient if its running time is polynomial. So any questions? I think this is a very important conclusion. I mean, intuitively, and also I think a very important thing that you want to talk about polynomial time rigorously throughout this course. So this is very important. Is there any questions here in class or online?
Many of the machine learning algorithms not following this, but on more computational reasons.
Well, yeah, that can happen. I mean, you just like try out your power. I mean, yeah, that is okay. But in general, I mean, from a theoretical perspective, I guess it is just like the beauty of a polynomial time algorithm that actually in general works well. But it is the case that maybe some algorithm, in the worst case, it maybe, for instance, take exponential time. But even some algorithm can magically work well in practice for most of the instances. Yeah, this can happen. Yeah, but as I just mentioned, like what is most of instances? What is like average case performance? It's not that easy to figure them out very clear. Could you scroll the little bit up? Sure. Oh, so there is a question. Isn't the running time of stable meshing n squared? This is a very good question. Actually, this is a very interesting question. So as if we want to look at precisely the running time, I mean the running time of this Gale-Shapley algorithm. So actually, I want to thank you for raising this question. This is not something that I want to get into super details today. And actually, you see like I'm being cautious. I'm saying like the number of well loops is at most n squared. But actually, you see that only looking at this algorithm. So this student actually has this kind of list that in general, like the first school LSE to which has not proposed, and then make the propose, etc. So in general, having this list and like try each other, this can be actually this is not something quite trivial. I mean, the number of well loops is not exactly the running time, but there are good data structures for the Shapley-Gale algorithm that can make the problem runs basically in square time. And this is actually in the textbook if you want to look at the details. So I think the main reason that I want to, and actually this is also textbook bringing into this stable meshing problem is that I want to make this as a showcase that in general, what is like the style of the class that we talk about like a model, a problem, and basically want to give efficient algorithms. Yeah, and actually it is, and thanks for the students for raising this. And yeah, the running time of this very naive version of Gale-Shapley algorithm is not exactly n squared, but it can be made in square time. And this is more advanced than what we need in this class. And if you're interested, you can check the textbook.
This is a definition of efficient algorithm.
It is widely accepted, the polynomial time definition.
That means the polynomial.
Well, it depends on who you ask. I mean, if you in general ask theoretical computer scientists, I mean, they are going to tell you efficient. But I think for a lot of problems, actually, n squared is bad. I mean, like n squared or n cube is already not efficient. Depends on what kind of problem you solve. I mean, if you solve like a big data problem and the n here is a billion, then this is quite not so helpful. I mean, in general, I think even in machine learning, I think also a very important trend in current theoretical computer science study is that one sublinear algorithm that maybe for some big data problem, you don't even have to maybe taking a few samples, you get some sense of it. Yeah, this can happen. Yeah, but like what being efficient in general, you want to talk about like talk to theorists, this polynomial time algorithm is definitely well accepted. And actually such algorithm later in this class, we are going to teach complexity theory. It's just like the P class. Yes, this is widely acceptable. But in general, what is being efficient? I mean, you want to talk about like word of efficiency, then there are always like room of debatability.
Applications, sometimes if you like you don't really care about space efficiency, but you know, like in reinforcement learning, like they have big tables, they have big memory to store data, so they can reduce the rental efficiency to the cost efficiency. So would you care much about the cost of space efficiency?
Space efficiency is actually very important also in from a theoretical perspective. I think especially there are different types of algorithm that talks about space, like space complexity of algorithm. So in later part of this class, we will talk about the complexity class called P space. So P space is basically algorithm that can be solved in polynomial space. We will rigorously discuss in later of this class. But I think in general, there is a class of algorithm called a streaming algorithm. So for instance, maybe you want to consider like algorithms in network protocols. In general, I mean, in network settings, typically each set has very limited space. Maybe it probably cannot save a lot of buckets or maybe something like that. In general, we want to talk about algorithm. Maybe the running time is like linear or maybe n or n squared, but we only have log n space. Yeah, there are also actually some algorithm along that, but maybe of interest, you can do like a project for that.
Yeah, because I know there's some tabular because you can do constant time data extraction, but the space complexity still exponentially with the unit size. So like the dictionary structure is like you do constant time data extraction, but your memory requirements there's some like some computer science really cares the space complexity.
Yeah, it depends. I guess there are definitely algorithms where space complexity is also very important. Sure.
Does if the algorithm that the time is polynomial, does that imply that the space is also?
Yes, yes. Because it's just like maybe, I mean, just later in this class, we'll talk about Turing machine. If the algorithm runs in polynomial time, you just, I mean, if you work on something, I mean, if you do one step, you just like maybe have one larger space. I mean, if you can do it in polynomial time, of course, you can do it in polynomial space. But maybe for a polynomial space algorithm, the algorithm can take much longer time because you keep maybe utilize some of the space in a clever way, and the algorithm can run much longer for it. Oh, so there are some also questions online. Let me see. So the student asked like, don't understand what the constant c does in polynomial time. So you mean this c times n to the d here? I mean, it can be the case. Maybe for instance, this constant is large. I mean, maybe for instance, in algorithm, some kind of algorithm, maybe the cost is like 100 times n squared. I mean, this can happen. I mean, in some of the cases, maybe for instance, in the description of the problem, there is already some overhead, but after it is can be captured by a constant. So in general, we actually just in the next hour, I will discuss about like the asymptotic notation. So basically, 100 times n squared is, roughly speaking, can be regarded as the same as n squared in kind of algorithm design. Yeah, but in general, we have a C here just to make sure that it contains such kind of cases. Yeah, also, thanks for a student that explained this. Okay, so let's actually go into this, and actually to address this student's question that maybe a little bit, the C here is a little bit confusing. So maybe can we actually describe the running time of algorithm in a more transparent way? Yeah, this is basically something called a big O notation. So what are big O notations? So we talk about, we want to talk about the complexity of algorithm here. So we want to really want to make comparisons between the different costs. And if you want to, in general, want to make comparisons, they are going to be something like upper bound, lower bound, and of course, tight bound. To basically characterize whether an algorithm is better, worse, or maybe comparable costs among each other. So this is basically some definitions that I'm actually going to copy here. Let's continue. So in the past hour, we basically talk about that in general, we want to have rigorous definition of algorithm. And in general, we want to talk, we talk about efficient algorithms. So we want to be even a little bit more careful that we want to talk about the so-called asymptotic notation. So basically we want to characterize the upper, lower, and tight bounds. So let me read the definitions here. So we say like a function, like a function Tn as big O of Fn if there exist constants c larger than 0, sorry, this. Such that for L n larger than n0, we have n is smaller than c. So I guess I'm probably not going to write this again. We can just copy this. Let's do it like this. So here, if you want to represent the lower bound, the notation here is not omega, but it's not O, but omega, like this. In general, we write Tn is theta of Fn if Tn is both O of Fn and omega of Fn. So I guess this is really something quite analytical, and maybe let me give you some examples to actually explain this. So maybe let's just consider a case where like the Tn here. I mean, in general, when you consider some algorithm design problem, there can be some formula can be a little bit complicated. So for instance, maybe let's consider a case where Tn is 32n squared plus maybe this whatever like 17n, maybe plus like 100. this can maybe this can just appear in like the course of algorithms. So in general, let's thought about like what is Tn here. So you want to say that this Tn here is On squared. So here it may be a little bit complicated that you see that we have this kind of thing like not only like a constant C here, I guess a constant C here, you want to basically represent that they are actually around like the same level. I mean, maybe actually Tn is upper bounded by C times Fn. But what is the usage of the N0 here? So this N0 is in general that we want to, the way that we want to deal with this kind of ugly terms like 17n plus like 100. So in general, maybe you want to consider this case where actually we have been written that Tn is O of n squared, but why is this the case? For instance, we can just like see Tn is smaller than like 50n squared. But this is true only when we see like 50n squared is actually larger than some like 32n squared plus like 17n plus like 100. And this is maybe just like the case, maybe for instance, like 18n squared is larger than 17n plus like 100. And I guess this is probably going to be true as long as maybe like sin n is larger than 100. And actually this can be something much smaller than that. But as actually in general, when we want to talk about the cause of algorithm and basically such kind of formula, it is not so interesting to basically, we don't really want to consider such kind of like tedious calculations. But we actually see that basically this n squared is in general like a leading term, like n squared is larger than n and larger than constant. We want to have this n0. So basically, this is just like something like n0 here. We don't want to really get to in this kind of tedious things. In general, as long as we look at this formula, okay, like n squared is the leading term and is larger than the others, we can simply write here that the Tn here is O of n squared. And maybe we can also write something else. So given that the Tn here is On squared, you can also very naturally see that Tn here is On cubed, like On to the 4th power, On to the 5th power. Although I won't say these are really super meaningful, but these are literally something correct that I just, maybe you can just keep in mind. But also on the other hand, you can see like Tn here is like omega n squared. I guess this is probably easy to see that in general, like this 32n squared plus like 70n plus like 100. Of course, it is going to be in general larger than n squared. So in general, this basically this kind of polynomial thing is very transparent. That in general, you can see that the Tn here is omega n squared, and also of course going to be omega n, and of course going to be omega. And this is actually going to give the conclusion that Tn here is actually theta n squared. So I guess this is something actually transparent that in general, as long as you have like a polynomial factor, basically summation of polynomials in this kind of things, the easy thing is just that you look at the leading term and this everything just follows naturally. And we want to emphasize, we just give you some wrong instances to make sure that you didn't get confused. So the Tn here is not. Of course, it is not omega of n because you have the 32n squared here. And this is actually much larger than n. And it is actually not omega n. Thank you.
That's big theta. Tn equals big theta.
Yeah. I just like read this as like capital theta. Yes, big theta. Yes. So the Tn here is not O of n, not omega of n squared, and also of course not in a tight bound of like theta n. Thank you. This is not the case. So there is one thing that I want to emphasize, that there is something like we actually slightly abuse of the notation here. What do I mean by that? So you see that I just like, actually I write that maybe like this Tn equals to like O of n squared. But actually there are something that in general the precise, I mean, if we want to do everything rigorously from a mathematical perspective, is that basically a precise notation. It's probably we shouldn't use like the equal sign here. It's probably we should have been written like Tn like belongs to omega of Fn. So the equality here can give some confusion. So for instance, maybe like Tn here is like this one. And maybe let's just consider some T prime n here is maybe like, let's maybe just like written something random here, whatever. So in this case, Tn equals to n squared but T prime n equals to also equals to O n squared. But of course, Tn does not equals to T prime n. So you see, like this is actually why we say this is a slightly abuse of notation. That in general, I mean, the equal sign actually should have transit. In general, I mean, from a mathematical perspective, the equal sign should have transitivity. I mean, A equals to B, B equals to C, then A equals to C. But this is not the case for the big O notation. So in general, we want to be careful. So in general, I mean, it's just like probably not a very good habit of computer scientists. So we want to make sure that as long as there's no confusion, you write this. I guess maybe there's more like a computer science kind of things. I guess you don't want to tell like mathematicians if you actually use this kind of notation. Yeah, but in general, as long as there is no confusion, we just write this. But just keep in mind that you cannot like use the transitivity here. So you should probably be careful. And also for this big O notation, we want to make sure that we don't claim something meaningless. So what is like a meaningless, like a meaningless statement? So maybe maybe you just like, I just write this down and you look at this sentence. So any comparison based sorting algorithm requires at least O(n) log n comparisons. So did you see the issue of this sentence? I mean, it's not about like how sophisticated, I mean, like comparison-based sorting algorithms are, but is there any intrinsic problem with the big O notation here? Yes, yes. So if you want to talk about an algorithm requires a certain cost, it makes no sense to use a big O notation. In general, if you want to talk about how efficient an algorithm, it does not make any sense to use omega notation. So this is something we want to be careful because, for instance, it's just like by the definition of the big O notation here. I mean, it's probably like 1 is O of n log n. Are you saying that any comparison-based sorting algorithm requires at least one comparison? This is of course true, but does not really make sense here. So in general, I mean, like you want to be careful in general about we shouldn't use like requires O or maybe like at most. This does not make any sense. In general, we want to be careful. I guess there are some standard things that maybe we can talk about. But I mean, we mentioned that there is slightly abuse of notation that the equal of omega, sorry, the big O notation and omega notation here, there are some slightly abuse of notation, but there are still some kind of transitivity and additivity that here we just want to make sure. So there are still some kinds of transitivity and additivity. So what do I mean by that? So f equals to O of g and g equals to O of h implies f equals to O of h. I guess this is probably straightforward. I mean, if you just like think about this, I mean, this Tn here is O of n squared, and maybe something of n squared is O of n cubed. Then of course your Tn here is going to be O of n cubed. So maybe let's actually give a very brief proof here. So we know that f is smaller than c times g for some for n at least n1, and also we know that g is smaller than, maybe let's just write a c1 here, smaller than c2 times h for every n at least n2, then we actually this 2 is going to imply that f is smaller than c1 c2 times h for n larger than the max of n1 n2, and this is a constant, and this is of course the max of two constant is still a constant. So this just implies the transitivity here, and of course you can just replace this by omega theta. So how about additivity? This just means that F equals to OH, G equals to OH, implies F plus G equals to OH. And similarly, we have this omega and theta, and also omega and theta. Any questions? I guess this should be relatively straightforward. Okay, so these are like very standard properties of the big O notation. So let's maybe as more examples, let's talk about some common functions. So the very first thing that we can talk about is, of course, polynomials. So we have like a polynomial, maybe like a0 plus a1 times n plus a2 times n squared, etc., plus ad times n to the d. And here we have the assumption that ad is larger than 0. So in this case, we can safely write this polynomial as big theta of n to the d. I guess this is relatively apparent based on the discussions that we made about. And basically, we can slightly shorten down the definition of polynomial time. So basically, for polynomial time, an algorithm is just like an algorithm whose running time is O of n to the d for some constant d. And of course, this should be independent of the problem size n. So how about some other functions? Maybe for instance, like the logarithms. So we can talk about a function maybe like this. Log n with a as the base. So in this, we basically, there are some basic mathematics here. So we, a standard thing is we write this log e of something, sorry, log. We write this log e of some x to typically we write this as log x. So e here is the limitation. It's just standard calculus thing. So this log n with a as the base just equals to log n over log a. And we can just like, I mean, for every constant a here, I mean, if a here is a constant larger than 1, then this is theta of log n. So this is actually a reason that you see a lot of in a lot of algorithm design analysis, we just typically write like n log n. So maybe a question is that what is the base of log here? I mean, this is not a question. I mean, it can be like log 2 of n or maybe like log 100 of n, but this really does not matter in terms of the big O notation. So this is actually a main reason why in algorithm design, we typically just like feel free to write log n here, just like we drop off the things. So here we have like the theta of log n, but we typically just simply write this as theta of log n. And I think on the other hand, maybe you want to talk about something a little bit larger, maybe about exponentials. So for exponentials, for any r larger than 1, in every d larger than 0, I guess you can see that n to the d is actually O of r to the n. So maybe just, even if this is like 1.01 to the n, this is in general larger than n squared. So this is also something a standard from standard calculus. And this just means that exponentials are typically faster than polynomials. I mean, we just want to emphasize this more. It's actually faster than every polynomial. Because it actually does not matter if it's like larger than n squared, but if this is like maybe say 2022, this is also true for sufficiently large. I mean, we have this notation. I mean, in this big O notation, we have this n0 here. I mean, in general, for this like a 1.01 to the n larger than n to the like 2022, then this probably really needs a large n. But for ultimately, I mean, from a standard calculus, you know that this is going to be true. So any questions? Sorry?
There was O0.
You mean wish O0? I'm not sure which one you are talking about.
So you're all the locations, yes.
Right.
So it's exponential. So maybe I misheard.
There does not make sense to talk about. I mean, it's not does not make sense. So the omega of O, or maybe the big O of zero is not so important, because let's just imagine that maybe you want to talk about something like omega of zero. Then it's just like something maybe as long as your n is larger than zero, you want to talk about some like function is smaller than. Oh, sorry. I think it probably terminates for a while, as long as probably or the internet connection is not stable. So issue here. It's connected. Maybe let me share the screen again.
I mean, the one means that it's constant time over.
You can write big O of one, but that does not make much sense to write omega or big O of zero. So you see, the point is that if it's constant time. Okay.
I think you should say the worst running time is valid. Constant.
Sorry.
That's how you say
It's
it.
the long.
It's the other.
Yeah.
When you're talking about big O, it's like saying that the worst running time least statuses. Yes, so if you have algorithms that is long by constant time, it's actually pretty good.
Yes. So if an algorithm is bounded by constant time, you can write like Fn here is smaller than some constant times one. And this just means this Fn is like big O of one. Right. Yeah, but if you for instance consider some big O of zero, then Fn is smaller than C times zero, but this is always zero. So this is not really something interesting. Okay, so any other questions? Okay, so I think this basically finishes the basic definition of asymptotic notations and basically how we are going to describe algorithms. So I think for the rest of this lecture and the next lecture, we are going to talk about graphs. So what is a graph? So graph is in general basically something like this. So we have like a graph G equals to like a vertex and edge set. So in general, we have some vertex, maybe something like this. So the graph is basically this V is typically called a vertex set. And usually we need to describe the problem size. And typically we use the N here to describe like the number of nodes here we actually have. And typically we also write we write the cardinality of E, the number of edges, as N in general. Yeah, so why do we want to consider such kind of things? So the edges maybe let me edges is basically from the set E here, and basically connects to vertices. So the graph is a very basic model because in general it has the good property of actually it captures like pairwise relationships. And also in terms of like pairwise relationships, because we are talking about something discrete. I mean, this vertex set is actually a discrete set. We have like 1, 2, 3 to the end. We have this number of vertices. In general, we can say that this relationship between discrete objects. Maybe for instance, I mean, we have a class here. Maybe like example is that maybe like the friendship. Maybe it's just like the V here is the set. Oh, sorry. The V here is the set of all students. And the N here is the number of students enrolled to this class. This class. And the M and the edge set here is the there exists an edge. If and only if maybe let's say there is an edge. Maybe let's say between Vi and Vj, if and only if like the students representing Vi and Vj are friends. So I guess this is transparent, and in general, you can see like this graph really captures a lot of things. As long as we have like disparate objects, I mean like students, I mean like professors, I mean in general, maybe some courses, you can talk about like those kind of relationships, and in general, you can see this kind of graph is really powerful that can actually characterize a lot of different things. So maybe for the example, maybe we can actually give a little bit more example like graphs. I mean like we can have nodes. In some of the textbooks and in some of the scenarios, the nodes are also called the vertices and also the edges. So we what we basically talk about is more like a social network, a social graph, and basically the nodes are people and the edges are relationships. But there can also be some other graphs. Maybe let's talk about like the World Wide Web. So in that case, I mean the nodes can just be web pages. Like the edges are hyperlinks. And there are also some other natural graph. For instance, we can talk about like transportation graph. And like the nodes are like stations and the edges are like the roads. So I guess these are relatively natural. So I think it is very important that in graphs, we want to be careful about like the two parameters, the number of vertices n here and the number of edges m here. So for instance, maybe let's take a close look at this graph. So this graph, like the left-hand side here. So what is the number of vertices here? Yes, exactly. And what is the number of edges here? I guess we have 10 edges here because we have like three triangles and like a separate edge. So like m here equals to 10. So here you see like we have this nodes and edges. So the next very important thing is that how do we represent the edges? I mean, I think a typical way is that we because we use n to describe the problems, basically the vertex set. I guess for instance, we can just feel free to maybe give some numbers, maybe call this like the 1, 2, 3, 4, 5, 6, 7, 8. Maybe let's just like number this graphs, basically the vertex of this graph in such kind of ordering. But after that, how do we represent the edges? I mean, there are different ways that given like the ordering of the vertex that we can store the edges. So this is basically something we want to be careful about. And I think maybe a very first thing that you can think about is something called the adjacency matrix. So what is the adjacency matrix? So the adjacency matrix is basically an n by n matrix with a uv equals to 1 if uv is an edge. So there are something we want to be careful about. And maybe for instance, let's take this as an example. Let me copy this. So in this case, what is the corresponding adjacency matrix? Let's just like draw this. So I think the first safe thing that we can write is maybe let me write the columns here from 1 to 8, and also the row here from 1 to 8. So the first safe thing that we can say is that all the diagonal elements, they are 0. Because in this graph, we really don't have self loops. I mean, like there is not an edge between 1 and 1. There is not like loops on that. Or maybe let me actually move this a little bit. down here to give a better. Yes. So the first thing is basically, of course, on the diagonal, we are going to have all 0 entries. And after that, we just like place all the edges correspondingly. So I think the first thing we notice is that each edge is actually represented twice. So for instance, we know that there is an edge between 1 and 2. But in this matrix, because we are saying that AUV equals to 0 as long as there is an edge. But from this graph, this is called an undirected graph because there is like no direction. There's no distinction between like from 1 to 2 or 2 to 1. In this case, you see like in these two places, there are actually both of them are going to be a 1 here. And similarly, we can mark them carefully. I mean, we can, for instance, like there are also an edge. Maybe let's actually do this. So we have done like 1, 2, and we can actually do 1, 3. And in 1, 3 here, or maybe let me actually do like the red colors here. 1, 3. And let's maybe, for instance, then look at 2, 3. And then maybe let's look at, say, like a 2, 4 here. The 2, 4 here is actually going to be this and this. And then it's going to be 2, 5, which is actually going to be this and this. And then it's going to be 5, 6. It is going to be this and this. And 3, 7. 3, 7. It is going to be this and this. And then it's going to be 3, 8. It is going to be this and this. And then 7, it is going to be this and this. And all other places in this matrix is 0. So is there any questions? Sure. Sure. You can have them. And for instance, maybe you should have self loops like this. And maybe you have 2 edges like this. Then in this graph, it should be there should be a 2 here. And here, I mean, the 1, 2 and the 1, 2 here is basically. Maybe let me also use a red color here. Should be like this. Yes, you can have this, but I think basically for the simplicity of algorithms in this class, we mainly talk about simple graphs. We talk about like maybe let me write simple graph. Graphs without self loops and multiple edges. So on simple graph, you can only have like in the entry of the adjacency matrix, you can only have 0. Okay, so let's talk more about like the adjacency matrix. So apparently, as we have been written this down, each edge is actually represented twice. And furthermore, there are some further things we want to be careful. So basically checking if UV is an edge. X theta E is theta 1 time. I guess this is also apparent because you just need to look into the table and see whether that entry is 0 or not, or 1 or not. This is just apparent. But I think the downside of the adjacency matrix, I mean, there are actually some downside, and maybe let's see that, because it's just like identifying all edges. Takes theta n squared time. So we want to keep in mind that the number of edges in general, I mean, in the very worst case, I mean, if you consider like the complete graph, it's just like all the vertices are connected. All the vertices pairs belongs to E. So in this case, the cardinality of E equals to n choose 2, and this is indeed theta n squared. But there are also many sparse graphs. I mean, there are actually a lot of graphs where there is not a lot of edges in this graph. And in general, I mean, identifying all edges takes theta n squared time. And basically you need to really read into this matrix. For instance, you can probably only need to look like one side. I mean, like maybe for instance, like this triangle. I mean, suffices that you look at into this triangle, you check all the entries and you get what this graph is. But for instance, if you don't like this, if you don't know, don't check this entry or not, you actually don't know whether there is an edge between vertex 1, 6. So that's the reason why I'm saying that identifying all edges takes theta and square time, and this can actually be worse than the total number of edges m here, which is not something so good. And also on the other hand, the downside is that it takes O in squared space. I mean, this is a capital O here. I mean, it's like a big O here. I mean, I'm not writing like a theta here because maybe if your graph is super sparse, I mean, probably like the number of ones here is not as much as the same level as like n squared. There can be maybe you don't need to take a lot of spaces. But really, in the very worst case, I mean, if this is like a dense graph, I mean, for instance, like the complete graph, like everything is one here, and storing it, of course, is going to take n squared space. So this is not something so good, and maybe we want to think about some other models. So maybe let's talk about something else, some other models that we can store the edges in a graph, and this is a model called adjacency list. So the adjacency list model, basically we have node indexed by by area of lists. So what do I mean by that? So let's maybe just take another look at this graph. I mean, I'm talking about simple graphs, so is not exactly this one, but it is this one that we just talked about. And 1, 2, 3, 4, 5, 6, 7, 8. So basically, for this adjacency list model, we are going to store something like this. We basically look at each vertex here. So for the vertex 1 here, we know that 2 and 3 is its neighbors. So we are going to basically draw something like that. So basically at the vertex 1 here, we store 2 elements that basically are 2 and 3 here. So basically also for the 2 here, we can store something like 1, 3, 4, 5, because apparently 2 has these 4 neighbors. And also for 3 here, we are going to have this 1, 2, 7, 8. And I guess for the 4 here, we are going to have the 2, 5. And for the 5 here, we are going to have 2, 4, 6. And for 6, we are going to have 5. And for 7, we are going to have 3, 8. And for 8, we are going to have 3, 7. So you see that the thing is actually getting stored is quite different compared to the adjacency matrix model. This adjacency matrix model, we actually store a matrix here, but adjacency list here, we basically store a list at each vertex. So how should we understand this? So in this adjacency list model, we also want to emphasize, I mean, the first point we talked about for the adjacency matrix is the representations. But here for the adjacency list model, you can also see that each edge is represented twice. So why is that the case? So maybe let's, for instance, like take a look at the edge 1, 3. So the edge 1, 3 is stored here. So basically, it's stored here in the adjacency list of 1 here. And also the edge 1, 3 is stored in the adjacency list of 3 here. So apparently each edge is also represented twice. And I think the downside of the adjacency list model is that checking if UV is an edge and takes the big O of degree of, can take this number of time. Where here this the degree of U here is the number of neighbors connected to U. So I guess this is also something relatively easy to comprehend, because you want to talk about like whether UV is an edge. But if you look at the adjacency list, and maybe here is like, for instance, you look at the adjacency list of 3 here, then there are 4 elements. And maybe, for instance, you want to ask like whether like 3, 7 is an edge here. So in practice, I mean, it is called adjacency list. And typically it is stored, I mean, there's like a main arrow here, but you can actually draw some small arrows inside. I mean, to actually check whether, for instance, like 3, 7 is an edge, you just check the adjacency list of 3 here. You see like, oh, the first element is 1, the second is 2, the third is 7. Okay, this is what you need. And also on the other hand, maybe you want to check maybe like 3, 6 is an edge. You also go into the adjacency list, you check, okay, the first element is 1, the second is 2, and third element is 7, and 7 is larger than 6. So this is not ideally like this is basically telling you that the 6 here is not an edge in this graph. So basically you can store this as like a list kind of structure. And that is the reason why I'm saying that checking if like UV is an edge takes O of a degree of U time. But there are also some good things. So basically identifying all edges takes O of m plus n time. So we want to be a little bit cautious here. I mean, for instance, maybe let's just talk about this graph. I mean, if this graph only has like one edge, maybe let's just talk about this 4, 5, 6. I mean, this is also a graph. I mean, although this graph only has one edge. So for this graph, I mean, you can see like the bottleneck is actually n here because you actually have like, at least you have n a list here. Basically, you need to have a list for each vertex. But basically, the adjacency list of the vertex, I mean, from 3 to 8, they are all empty. I mean, basically, there are only elements for the 1, 2 here. But you need to create this adjacency list for this vertex. So that is why we actually have an n here. But on the other hand, when you want to look at like the things inside this adjacency list, I mean, I guess it is apparent that basically the number of elements here are on the right-hand side. And actually, you can prove that the number of elements in all adjacency list exactly 2 times n. So why is this the case? So just like, for instance, you look at this graph has 10 edges. And like this is like 2, 4, 4, 2, 3, 1, 2, 2, and you plus them together. This is like 6, this is like 10, 12, 15, 16. Yeah, you sum them up, then equals to 20. This is actually quite straightforward because as I just mentioned here, each edge is actually represented twice. And all the edges, I mean, each edge is represented twice. And if there is not an edge between 2 vertex, and does not make any contribution. So that's the reason why the number of elements in all the adjacency list equals to exactly 2 times m. And also this also implies that identifying all edges takes O of m plus n time. But here, I mean, in this lecture and in the next lecture, we are going to write a lot of places where the cost is O of m plus n. And maybe some of you are actually getting confused. I mean, in general, I mean, in most cases, m is larger than n, but we want to be careful about some extreme cases. So that is the reason why we write like O of m plus n here. And also, the space complexity of the adjacency list is actually O m plus n space. So I guess this is clear, and I think I probably have 10 more minutes. So maybe let me give a little bit more definitions here and actually call the end of this lecture. So the next definition we are going to talk about is path. So a path is basically a path in a graph G equals to VE. Is a sequence of, is a sequence of nodes V1, V2 to Vk such that Vi plus 1 belongs to the edge set for arbitrary I belongs to. In this class, we write this notation. So we run I belongs to k minus 1. And basically, in general, we write like whatever, maybe you write over k here. This represents the integers 1, 2, 3, etc. to the k. And of course, here, if you write this as this bracket k minus 1, this represents the integers 1 to k minus 1. So for example, in this graph above, basically, I mean, 1, 2, 4, 5 is a path. And similarly, I mean, you see the path here, and there are also triangles, and the triangles here are typically called cycles. So this definition is basically the same, except it has the requirement that the end, that basically Vk, V1 also belongs to the edge set. I guess this makes sense because path is just like a line that you move from one end to the other end, but cycle really means everything is actually getting close. So basically here you see this like 2, 4, 5, and this is basically a cycle because the 5 actually can also go back to 2. This is like a cycle. So any questions? Yes, it allows. Yeah, this is an interesting question. So a student asked like whether a path allow like the same vertex along this line. So you see by the definition, we didn't assume this. In path, so if for arbitrarily I not equals to j, vi not equals to vj, we call this, I think we call this a Hamiltonian path, if I remember correctly. Oh, sorry. I probably made a mistake here. So I think typically when we talk about path, we don't have this restriction, but there is a definition called a Hamiltonian path. Sorry, I need to be a bit more careful. I think a Hamiltonian path is you really need to traverse all the vertex such that for arbitrarily I not equals to j, vi not equals to vj, and also vi plus 1 belongs to e for arbitrarily I belongs to n minus 1. This is called a Hamiltonian path. So basically, maybe in later part of the class, we will probably talk about the problem of finding a Hamiltonian path. And in general, this is a very difficult problem. And in general, the emphasis of like the vertex being different on a path intuitively is something quite hard. Okay, so I think the last definition that I'm going to give today is called trees. So the tree is an undirected graph, which is connected and does not contain a cycle. So maybe let's make an example for this. So this is basically a tree. So I guess apparently you can see this is a tree because it is connected. I mean, all the vertex you can, I mean, from one point to another, but this graph does not have a cycle. And having a definition of tree, there is also a closely related definition called a rooted tree. So given a tree T, choose a root node and orient the edge from the edge away from this. Maybe let's just call the root node R, then we orient the edge away from R. So what do I mean by that? Maybe for instance, let's just assume that this is the R here. So this is the tree, and then this is a rooted tree. It's going to be something like this. So let's maybe, for instance, take a look at this component. Then basically it is going to be something like this. And maybe, for instance, how about this component? It is going to be something like this. And if you look at the rest of the graph, it is going to be basically looking like this.
I think in your edge, it says V, I mean, the edge between VI and V
No, I'm writing I here, I guess. Maybe you're not seeing it clearly. So this is basically, you can see, I mean, if I look at this very specific point as R here, you can regard this tree, you can like rearrange it. I mean, look at in from another perspective, it's basically the rooted tree in this right-hand side. So I think I'm basically running out of time, and I think the next week we are going to talk about like more on graphs and also some graph algorithms. And in retrospect, basically what we discussed about this lecture. So in this lecture, we talk about, I mean, of course, at the beginning, we talk about like the basically the organization and the things we are going to cover in this class, and basically how we are going to evaluate the class. And I think we basically have this very specific example of stable matching. So I guess this stable matching, although it's I mean, we discuss a lot about this. I mean, they are this is really like a toy model, but I think this is basically give some inspiration about in general about what algorithm design is and basically the things that we want to study. Then basically in this class, we actually also introduce the asymptotic notation. So what are efficient algorithms? And basically we have this big O notation, omega notation, theta notation to represent the upper, lower, and tight bounds respectively. And I think basically for a little bit of this lecture and also the next lecture, we will be actually talking about graph algorithms. And I think more details will be covered next. So is there any question? Okay, so if there is no question, thank you for attendance and see you next week.